Hey there, guys. It's Mr. Sheeline. We're going to be getting into Unit 2.3 notes. These notes are going to be pretty quick, or at least relative to other notes that we've done. It's going to be pretty quick. So, Unit 2.3 notes models of atoms and their uses. So, let's just get straight to it. So, here are your learning objectives. So, your learning objectives here is that I want you to at least recognize or at least or identify two out of the four individuals responsible for the modern atomic structure and summarize their accomplishments. I also want you to be able to configure subatomic particles into the Bohr model and understand why Thomson's model was inaccurate and why Bohr's model represents an atom more closely today. So, for the most part, as you saw in the video over the past weekend or on Monday, whatever you watched the video, it was a crash course video I'm mentioning. Scientists such as John Dalton, J.J. Thomson, Ernest Rutherford, and then Niels Bohr made mountainous discoveries that allowed us to understand the atom that much more. So let's kind of recap. These notes are more of a recap of what they did. So John Dalton. Okay, so John Dalton's theory was that he gathered evidence for existence of atoms by measuring the mass of elements that could be combined together to form a compound. So because of this, and because he was able to also show that compounds formed always had the ratio of masses on the elements, he's credited a little bit with coming, or at least contributing to the law of conservation of mass. Now, of course, Antoine Lavoisier was the one who pretty much devised that idea. Dalton pretty much solidified it because Dalton noticed, hey, wow, if I add these two things together, at the end of it, I'll have the same mass with my product than I did with the two things I just added together. So, as an example, it'd be like if you were baking a cake, and while you're baking a cake, in the process of it, you're gathering up all the ingredients. Let's say that you measure the mass of the flour, the eggs, or at least the eggs, parts of the eggs you'll use, the water, milk, baking powder or baking soda, I should say. If you find the masses of all of those, you add them all up together, and then you mix everything together. You dump it in the pan, and then you bake the cake. Relatively speaking, you will have, or you should have, the same mass from what you started with and then also what you ended with. And that's pretty much what the law of conservation of mass was. And not only that, but what Dalton really showed was like, well, all the stuff, all the ratio of the stuff you have in the beginning, you'll have the same amount of stuff at the end too. And we'll get into what that looks like in a chemical equation in the next set of notes. But anyway, this is what we can contribute him to doing. Now, again, he didn't devise the idea of law of conservation of matter. He more or less solidified it. Okay. So here are some other included ideas. So all matter is made up of individual atoms, the atomic theory. Compounds contain atoms of more than one element, and atoms of an element have the same mass. So if you got two atoms, to talk about the last one, it's to say that if you have two isotopes that are exactly the same isotopes, they will both have exactly the same amount of mass. Okay, that's what he's saying there. So those are Dalton's contributions. So here's J.J. Thomson's contribution. So he discovered that while he was working with electrical currents and he wanted to know how atoms, are affected by these currents, he more or less discovered the electron. So he was a guy with the cathode tube, the cathode ray, where he was wanting to find out about the heat and how much they would bend in a cathode tube with the cathode ray. Oh, excuse me. He wanted to. He's a guy that pretty much was like, "Hey, that's kind of weird. It looks like my cathode ray bends towards a positively charged end of a magnet, but then it does the opposite for a negatively charged end of the magnet. So that's kind of weird. So there must be negatively charged things in particles in this cathode ray, in this cathode tube." And that's what he pretty much did, and he found out they were electrons. And what he did with that information is that he then was like, well, if this is true, then it must be then because at this point, atoms were pretty much considered to be a thing, or at least super duper tiny particles that make up all matter. He's like, well, that must mean then that these little atoms, they must be a positive matrix or this kind of positive body, and within it are all these little negatively charged things, kind of randomly dispersed, and that's what's pulling my tube, or pulling that ray up towards a positively charged magnet, or those little negatively charged things in there. Okay. Oh my goodness, excuse me. He proposed what was referred to as the plum pudding model, or the chocolate chip ice cream model as well, or chocolate chip cookie model. Okay. And then there's Ernest Rutherford. So Rutherford is a guy who pretty much he had uranium, and he's like, wow, this is really cool. Uranium emits all of these particles, and isn't this so cool? It's decaying, and this is awesome. So he used the alpha particles that were decaying off of the uranium, and he beamed those alpha particles and shot them at gold foil. He had a thin sheet of gold foil, and for the most part, he expected them to pretty much just go straight through. That's what he expected. And but what he discovered was that pretty much the atom is composed of nothing but empty space. And not only that, but he discovered the nucleus, and that's the dense positively packed center of the atom. And he was like, well, that's pretty neat. So because the alpha particles are positively charged, and if the nucleus is pushing or repelling, they're repelling all of this stuff. That must mean then that the center of the nucleus must be, mostly positive. And he was right. That's where those protons come in. So he could be credited with discovering the nucleus. Oh my goodness, I have yawned like 5 times. God bless. I am so sorry. And then last, we've got Niels, however we pronounce his name, Bohr. We got Mr. Bohr here. And Bohr was like, okay, so we've got electrons on the outside, we've got protons on the inside, and eventually, confirm there's another scientist that confirmed neutrons. But we've got a net positive charge in the nucleus. We've got the electrons negatively charged on the outside. Only problem is there's no way that these guys can, those electrons can all sit outside of the nucleus all fine and dandy without having to arrange themselves in a particular manner. So what he came up with is that he was like, well, they have to be a particular distance away, because there's too much force between the negatively charged electrons, between the negatively charged electrons, and also the repelling force of from the positive protons pushing against one another. Like there's just no way. Like they would be unstable, and we just have energy floating around everywhere. So they have to be arranged in such a way that allows them to keep their composure, but allow them to not just fly everywhere and bump into everything. So he devised this system of orbitals, or energy levels, that electrons could reside in with a specific abundance or population. Okay, and how he described that is the Bohr model. It's also called the planetary model, and this is the one that you've been working on since middle school. And it's pictured right here. So if you look at my mouse over here, it's this guy over here. And it's to say that here's your positively charged nucleus, here are your electrons, and there's a specific number of electrons that can fit outside of the nucleus. And not only that, a very specific distance. Now, what Bohr wanted to do, though, is that Bohr wanted to take this information. He wanted to accurately predict exactly where these electrons were going to be at any given moment with any given atom. And eventually that was shown not to be true. That was where Heisenberg came in, and even Schrodinger were like, dude, you just can't do this. And then Schrodinger and both Schrodinger and Heisenberg more or less devised the idea that there's quantum material here that is calling the shots, and how they arrange themselves into different, how atoms arrange themselves into different shapes, and how we can expect to see, we can maybe make some decent probability, or we can have probability of saying, like, we expect to find electrons in this particular spot, if it's this particular isotope under these particular conditions. And that's mentioned in the video. I don't go into it, because we stop here at Bohr. But pretty much they just told Bohr, yeah, it doesn't work like that, man. You mathematically cannot do it. Physically cannot happen. And as the video also mentioned, is that once you know the position of one particular particle, it's increasingly more difficult to find the position of another particle, which is basically just to say that there's so many variables that go into it. As soon as you calculate one variable, there's probably, for every one variable that you solve, there's 100 more that are possible, and it's just impossible to figure out where one is at a particular time. So anyway, so those are the notes. If you have any questions for me, make sure you ask. Go into Google Classroom, make sure you are caught up with all your work. Email me or text me on Remind and ask me if there's anything missing. Talk to me in class if you have any missing assignments. And that's pretty much it. So if there are no questions, I will catch you guys in the next one.